Now there's a theorem. This is the handshaking theorem, and it says that if G is a graph with m edges, so if G is a graph and it contains a certain number of edges, which is m in this case, then the summation of the degrees of all the vertices in the graph will be equal to 2m. So the summation of all the degrees of the vertices in the graph, which is this one, will be equal to twice the number of edges present in the graph. So to prove that, I will be explaining that with an example. So this is an undirected graph, right? So the degree of A is equal to 2. The degree of B is also equal to 2. Degree of C is equal to 2. And degree of D is equal to 2. So the summation of all the degrees is equal to what? Is equal to 8. And here m is equal to the number of edges, right? 1, 2, 3, 4. So there are 4 edges. So the summation of the degrees of all the vertices in the graph is equal to 8, and it's twice the number of edges in the graph. So this theorem is proved. But why is this case? So let's discuss that. So for a certain edge, for one edge, you can see that you're counting degree once here and you're counting degree once here. So for a certain edge, you are counting the degree 2 times. As a result, if there are 4 edges, then the total number of degrees will be equal to 8. So you can see the proof is an edge UV is counted twice in the above summation. So it's counted twice, and once by its endpoint U and once by its endpoint V. So one edge is counted twice while counting the number of degrees. Thus the total contribution of the edges to the degrees of the vertices is twice the number of edges. Now let's discuss this particular theorem. It says that if G is a directed graph or a digraph with m edges, then summation of the in degree of all the vertices of the graph will be equal to summation of the out degree of all the vertices in the graph, and this will be equal to m. So let's discuss this with another example. This is a very simple example. You can see that I have only 2 vertices in my graph and a single edge. So let's count. This is an edge, so the value of m will be equal to what? Equal to 1. So in this graph there is only one edge, so the total number of edges will be equal to 1, and hence m will be equal to 1. Now let's check the out degree of A. Out degree of A is equal to 1, and in degree of A is equal to 0. In the same way, out degree of B is 0, and in degree of B is 1. So you can see that the summation of out degree of all the vertices in the graph is equal to 1 plus 0, 1, and the summation of all the in degrees of the vertices in the graph is equal to 1. So summation of out degree is 1 and summation of in degree is 1, and m is also equal to 1. So all of them are 1. So this proof is satisfied. It says that if G is a directed graph, which was a directed graph in my example as well, the in degree is equal to the summation of the in degree is equal to 1, the summation of out degree is equal to 1, and this is equal to the number of edges 1. So I can relate the theorem with this example as well. Now, why is this case? Because in a directed graph, an edge UV contributes 1 unit to its out degree of its origin U and 1 unit to the in degree of its destination V. So if we consider this particular edge, you can see that this edge is contributing once for the out degree of A, and it's contributing another time for the in degree of B. As a result, the summation is equal to 1, and the in degree summation is also equal to 1, and the total number of edges is also equal to 1. So the total contribution of the edges to the out degrees of the vertices is equal to the number of edges, and similarly for the in degrees. Now let's look into this theorem, which says that if G is a simple undirected graph with n vertices and m edges, then m must be smaller than or equal to n into n minus 1 by 2. Before starting this theorem, you need to keep two things in mind. The first one is m represents the total number of edges in a graph, and n, which is this one, represents the total number of vertices in a graph. Another thing you need to remember is this particular theorem, which I discussed previously. It says that the summation of the degree of all the vertices in the graph is equal to twice the number of edges. So if you remember these two things, we can start the theorem. First, you need to find out the maximum possible value, of total degree of all the vertices in a graph. So you need to find the maximum possible value of the total degree of all the vertices in a graph. So the maximum value is only possible when each vertex in the graph is connected with all other vertices. So let's look into this particular example, which is this is an optimal graph, and you can see that in this graph each vertex is connected with all the other vertices. Similarly, B is connected with all the other vertices. D is also connected with all the other vertices. When this happens, each vertex has the maximum possible degree, which is n minus 1. So I said you to remember one thing, which is n and m, right? N represents the total number of vertices, and m represents the total number of edges. So each vertex is connected with all the other vertices. So each vertex is connected with n minus 1 vertices. So the degree of this particular vertex is n minus 1. Similarly, this vertex is connected with n minus 1 vertices, this vertex is connected with n minus 1 vertices, and this vertex is connected with n minus 1 vertices. So one vertex can have a maximum degree of what? N minus 1. So if one vertex has a maximum degree of n minus 1, therefore n vertices will have a maximum total degree of how much? N into n minus 1. So this is basic unitary method. So I have found out the maximum possible value of total degree of all the vertices in a graph, which is n into n minus 1. I told you to remember the theorem that I discussed previously, which said that the total degree or summation of the degree of all the vertices in a graph is equal to twice the number of edges. So this is equation 1. And another thing that I wrote in equation 2 is the total degree. The total degree of all the vertices in a graph can be either equal to or less than the maximum possible value, right? Maximum possible value is the highest limit. So the total degree of all the vertices in a graph can either be equal to the highest limit or can be smaller than the maximum possible value. So I have created two equations, equation 1 and equation 2. So if I put equation 1 into equation 2, then I can write 2 into m smaller than or equal to the maximum possible value, right? Now the question is, what is the maximum possible value? The maximum possible value is n into n minus 1. So 2m can be smaller than or equal to n into n minus 1. So I can rearrange this equation into m smaller than or equal to n into n minus 1 by 2. So I get this equation where m is smaller than n into n minus 1 by 2. So my theorem gets proved. M is smaller than or equal to n into n minus 1 by 2. So this explanation is also given in words. You can read it yourself, and it's quite self-explanatory. You can see that since G is a simple undirected graph without self-loops, the maximum degree of a vertex is equal to n into n minus 1. And since there are n vertices and each edge is counted twice, one for each end of an edge uv, the maximum number of edges is n into n minus 1 by 2. Thus, m can be smaller than or equal to n minus 1 by 2. So this is the proof of the theorem. You can write this thing as well, or if you want to break it down and understand it, then you can also use this procedure. Similarly, for directed graph, m is smaller than or equal to n into n minus 1. You can apply the similar or same process to prove this.